Alright, looks like we're live. Hello everyone and welcome to another Zuzin session. How about that? I bet you didn't expect that shit to happen. So today is the 8th day of AoC in HolyC. And before we start, we need to make a little bit of an announcement. Let me bring the Discord server super quick, just a second. Boom. So I'm gonna do a red circle. Live on Twitch, because that's where we are right now. We are on Twitch. And we're doing AoC in HolyC day 08, and I'm gonna give the link to the channel where I'm currently streaming. And I'm gonna ping everyone who's interested in being pinged, and there we go, the stream has officially started. The stream has officially started. Hello everyone, welcome. So, yeah. Let me take a look. So I'm gonna go into Advent of Code, and so let's take a look at the 8th day, shall we? So day 8, 7-segment search. 7-segment search. Okay, this one is interesting. You barely reach the safety of the cave when the whale smashes into the cave mouth, collapsing it. So whale smashes into the cave mouth. I don't really know what cave mouth means, but maybe it's like an entrance to the cave system. Okay, collapsing it. Sensors indicate another exit to this cave at a much greater depth. So you have no choice but to press on. As your submarine slowly makes its way through the cave system, you notice that the 4-digit 7-segment displays, 7-segment display, but there's clearly, yeah, there's a 7 of them. Okay, 1, 2, 3, 1, 2, 3, and here is the 7th one. There's also dot in here for whatever reason, but whatever. In your submarine are malfunctioning. They just have been damaged during the escape. You'll be in a lot of trouble without them, so you'd better figure out what's wrong. Flopper X3, thank you so much for 2 months of Twitch Prime subscription. Thank you, and welcome to our epic AoC in HolyC Club. HolyC. Okay. Each digit of a 7-segment display is rendered by turning on and off any of the segment named A through G. Okay, A, B, C, I suppose. A, B, C, D, E, F, G. Okay, so that makes sense. That makes a lot of sense. That's very cool. So to render a 1, I suppose it's a 1, only segment C and F should be turned on. The rest should be off. To render a 7, only segment A, C, and F would be turned off. The problem is that the signals which control the segments have been mixed up on each display. The submarine is still trying to display numbers by producing output on signal wires A through G, but those wires are connected to segments randomly. Worse, the wire segment connections are mixed up separately for each 4-digit display. Okay, all of the digits within the display use the same connection though. All of the digits within the display use the same connection. Okay. So you might know that only signals wires. So you might know that only signal wires B and G are turned on, but that doesn't mean segments B and G are turned on. The only digits that use 2 segments is 1, so it must be segments CF are meant to be on. With just that information, you still can't tell which wire BG goes to which segment CF. For that, you will need to collect more information. For each display, oh my god, I've already tired reading this entire thing. Okay, Pablina subscribed with Twitch Prime. Thank you for subscribing, and hello everyone. For each display, you watch the changing signals for a while, make a note of all 10 unique signal patterns you see, and then write down a single 4-digit output value you process input. Using the signal patterns, you should be able to work out which pattern corresponds to which digits. For example, here's what you might see in somewhere around like here. I kind of like lost track of what the fuck is it saying. Right, so it was just like, okay, maybe I'll have to read one more time. For each display, you watch the changing signals for a while, make a note of all 10 unique signal patterns you see, and then write down a single 4-digit output value puzzle input. Using the signals patterns, you should be able to work out which pattern corresponds to which one. For example, here is what you must see in a signal entry in your nodes. Okay, so cool. And there is this thing, I'm not sure what the fuck is that supposed to mean, so okay. The entry is wrapped here to 2 lines, so it fits in your nodes. It will all be in a single line. Okay, so is this thing indicates the wrapping? Okay, it is not, it's actually in delimiter. Each entry consists of 10 unique signal patterns, a delimiter, and finally the 4-digit output. With an identity, the same wire signal connection are used, but you don't know what the connections actually are. The unique signal pattern corresponds to 10 different ways the submarine tries to render the digits using the current wire segment connections. Because 7 is the only digit that uses 3 segments, DAB, in the above example, means that to render a 7 signal lines DAB are on. Because 4 is the only digit that uses the 4 segments EFB, means that to render F4, signals EF and B are on. Using this information, you should be able to work out which combination of signals wires correspond to each of the 10 digits. Then you can decode the 4-digit output value. Oh my god, I think I'm starting to understand what the fuck they're saying. Right, so this is basically the connections, right, that you have to use, and then you have to decode this thing to work out what the fuck is that. Right, if I understand correctly. So C defab. Though it's kind of like weird, but okay. So the digits in out with defab use 5 segments and are more difficult to deduce. For now, focus on the easy digits. Daily Coder, thank you so much for 2 months of Tier 1 subscription.
Welcome to Epic AoC Club.
You're damn right. Thank you. Advent of reading, by the way. For now, focus on the easy digits. Consider the larger example. B. Okay, so here's that and this one. Okay. So because the digits 1, 4, and 8 each use unique number of segments, you should be able to tell which combination of signals corresponds to those digits, counting only digits in the output values. The part after, in the above example, there are 26 instances of digits that use unique number of segments. Output value, how many times? What the fuck do you want from me? I don't even understand what the fuck do they want from me. It's so convoluted, intentionally, right? So... Holy shit, okay. So the puzzle input, I suppose, is just like a bunch of these things, right? So it's a bunch of, yeah, it is true that it's a bunch of these things. Cool. So these are the connections, right? And I suppose there should be like 9 of them, or maybe 10 of them. Right, there is a 10 of them for each individual digit in here. Okay, that's pretty poug, not gonna lie. So each entry consists of unique... Okay, for now focusing on the easy digits. Consider this larger example. FD, GCB, GCBE. Okay. Because the digits 1, 4, and 7 each use unique number of segments, you should be able to tell which combinations of signals correspond to those digits, counting only digits in the output values, the part after. In the above example, there are 26 instances of digits that use a unique number of segments highlighted above. In the output value, how many times do digits 4, 7, and 8 appear? Okay, so... that is very, very interesting. So, I want to understand, though, right, I want to understand what kind of... I think I need to actually start, like, you know, advent of code problem, right? So let's actually go ahead, because I want to start, like, sketching out things, trying to understand what the fuck is going on, right? AoC 2021. Right, I'm gonna run AoC 2021 image. Okay, I think I don't need to fetch any changes, hopefully. We'll see. We'll see how it goes. So here we are, and I'm gonna start a new day, a day 08. Day 08, there we go. So here is the day. So I also want to maybe zoom in a little bit so I can have a proper sketch somewhere here. So the number 0, right, the number 0, how many of this thing it is using? So it is very important for me to actually write that down. So there's literally like 6 segments. 0 uses 6, 1 uses 2 segments, and 2 is using 5 segments, right? So this is 5. 3 is using also 5. Okay, 2 and 3, they're using like the same amount of segments. 4, if I'm not mistaken, yeah, so they are using, so essentially move from one to into another one. 4 is literally 4. Right, so for the 5, we are using 5 of them. So 2, 3, and 5, they're all using 5 segments, which is rather interesting, actually. And 6 is using 6 of them, as far as I can see, which is rather convenient as well. Right, so 7 is 3, right, 7 is 3. 8 is all, wait. 1, 2, 3, 1, 2, 3. So 7 is actually 8. Right, 7 is actually 8, and 9 is 6. Okay, all of that kind of makes sense. So it's rather interesting. All right, so they say that the unique things are 1, 4, 7, and 8. 1. Okay, so I didn't really mean to click and actually screw everything up. So 1, then I want to actually take 4. So I'm thinking to sort of like put it like that. So 1, 4, 1, 4, 7. Temple OS, what the fuck are you doing? I'm just moving like mouse around and it's just like going fucking crazy all of a sudden. Okay, so this is the 7, right, so the 7, and another one is 8, right, which is rather easy. So these things are super easy to identify. So what's interesting about these values already, right, so 3 of them are 5 and 3 of them are 6. So this is a very interesting information that we can probably use in the future. Right, so we probably can do something with that information in the future, not right now, but yeah, sounds like something very, very interesting. Okay, guys, so, and I'm gonna actually mark this thing as unique. Not very unique, right? So we have something like this. And I suppose the part 1 is the easiest part. In the upper layer, how many times do digits 1, 4, 7, and 8 appear? So, yeah, you literally have to... Is the part 1 that easy? I feel like the part 1 is just like, yeah, ignore everything in here for now and just count these unique digits, right? And just give us the output. Is that the part 1? Because that's kind of... I suppose part 2 is going to be way more complicated. So I would presume that in part 2 you would have to recover the actual values, right? So you can use this information to get some, so these numbers to get some information about these connections, and once you get some information about these connections, you have to sort of reverse back and figure out the not so unique numbers, and yeah, and then provide some sort of proof of solution that you actually did that, or something like that. This is what I expect from the part 2 at least. So far so good, I think. I do not fully understand the problem though. I do understand what I need to print, but I do not understand all of the wire mumbo jumbo that they talked about. So I guess maybe that's intentional, right? So maybe intentionally the author wanted you to be able to solve the part 1 without fully understanding the problem, so they can hit you in part 2 where you actually need that understanding. So I guess that's the point here. Okay, anyway, so let's actually try to download the sample and maybe solve all of that. Okay, so I'm gonna actually close QEMA. So I'm gonna do mount, and it's gonna be AoC 2021. Okay, so then I'm gonna go here and into the home, and I hope the folder is gonna be there. Okay, so the folder is apparently here, so which is super nice. So let's take a look at the sample txt. AoC in HolyC. I'm sorry. What the fuck am I talking about? Well, this is not really what I wanted. So, can I just? Yeah, I just want you to do this. Can I? I cannot quit. How do I quit ed? Okay. I don't know how to quit ed. Okay. Just a second. So they're wrapped around, and that kind of screwed me over. Right, so essentially what I need to do, I can't just copy paste them, right? So I have to first unwrap them, which is super convenient. Thank you so much, author of this problem. Very cool. So let me quickly do that. I wonder if I can do something like this, right? So it's gonna be 3, and then boom, and yeah, 4. This is what I wanted. There we go. Cool. So then I'm gonna go in here. So this is gonna be home AoC 08 AD sample txt. Right. So and then I'm gonna provide this thing in here. So I'm gonna copy paste this stuff. Then I'm gonna save that. Finally. Ooh. Okay. So and let's get the puzzle input. More and more artificial difficulty. More and more artificial difficulty rather than the actual one. Just like in real life, by the way. Okay, real life simulation. This is not what I wanted, but that's fine, I guess. Because I can always just go there, maybe. Go into the input in Vim, right, and just remove that thing. Okay, cool. So then I'm gonna go in here, I'm gonna run AoC 2021, and let's actually do this thing. Cool, finally. It was hard, but we managed to do that. So 08. So here are the samples, right? So this looks like a sample. I hope I didn't actually screw anything up. And here is the input. That's a lot of shit in here, but surprisingly, like Temple OS is capable of handling all of that, right? So I'm super happy about this. So how are we going to essentially parse all of that? So all of those things are words, right? All of them are words, so that should be relatively easy to just use one of our common things. We have like a common module in here, right? And the common module allows you to chop a particular word, and word is anything that fits alpha, right? So it's alphanumeric thingy. So yeah, we can give it a try. So 08, and I'm gonna go in here. While SV size is greater than 1, right? So while SV size is greater than 1, and we're going to do the following thing. So we need to keep track of the word, right? So I'll need to allocate a thing like word on this stack as well. SV chop word, we provide the SV, and then we provide the word. So I don't remember if chop word actually returns anything, so maybe it's fine. Though we have like 10 words in here, so one of the things we'll have to do, we'll have to just skip the word 10 times, right? So I'll have to do something like 10 plus I, and essentially we're just skipping a word, but each word in fact is separated by one space, right? So on top of that we'll have to do something like SV chop left, and we can just use like default value, which is 1. So we're just basically skipping all of them. And after that, if we take a look at the sample, right, we also remove a single space. So after doing this kind of stuff 10 times, we're going to have 2 characters in here, which we can also skip quite easily. Right, so let me quickly do that. So SV chop left 2, and we're starting to actually parse the values, right? The output values. So, and in here we're gonna do it like this: 0, then 10 plus I, and so essentially, wait a second. Where is my breakdown of each individual number in here? Did I not save that, or did I accidentally press Shift Escape again? I think I accidentally pressed Shift Escape again, because that thing for like breakdown how many like bars do you need, for how many segments you need for each individual number is like very important for me, right? Because it makes me understand what the fuck is going on. So we'll have to do it again, whether you want it or not, right? So we'll need to do that. So let me quickly do that, super quick. So it's very, very important. So 0, as already said, is going to be 6, and then 1 is going to be 2. Right, is it 6? Yes, it is 6. 2 is 5, right? 3 is 5. 4 is 4, right? So because it's one of the unique ones. 5 is 5. 6 is it is 6. 7 is 3. 7 is 3. 8 is 7, right? 8 is 7, and 9 is 6, I suppose, right? So, and the unique things here are these ones: 4, 1, 4, 7, or 8. So the rest of them are not very unique. So it's like 3 5s and 3 6. Unique. Not very unique. Right, and I'm gonna save that. It's very important to save this thing, right? Because I'm using it for like mental stuff. Okay, so here we have to do 4 of them, right? So if I take a look at the sample, we have 4 of these things, which is cool. So this is going to be 4. And we can do the following thing. We can switch upon word. SV chop word. SV word, and then we want to do SV chop left. There we go. And if the size of the word, right, if the size of the word is one of those things, right, if it's one of those things, case 2, case 4, case 3, or case 7, we have to increment some sort of like internal counter, if you know what I'm talking about, right? So this is going to be count plus plus, and here we might want to break. Right, so that's basically it. The only thing we need to you know, allocate the counters. So I64. We might as well allocate I as well. Do we need to allocate anything else? I didn't think so. I didn't see any reason to allocate anything else, so that should be fine, I guess. So then we can print the part 1 situation in here. So this is going to be just D, and I just provide a count. Hopefully I didn't fuck it up, though I probably did, because I did not initialize the count, right? So we have something like this, and this is not what I wanted. I just wanted to save this entire thing. Okay, if I just try to run it, it does not even compile because we need to do 34, right? So let's take a look at 34, and what does it say? I don't quite understand what the fuck is it talking about. Missing expression, compile a parse error at semicolon, 34. I don't see what it's talking about. It's talking about something semicolon something. Chop left should work perfectly, but it doesn't. And I don't quite understand. Is it something with chop word, or is it something with chop left, or some stuff like that? Okay, so if I do chop word, we accept 2 pointers to the input and to the word, and chop left. Oh, chop left actually accepts the string that we're chopping. Okay, so I completely forgot about that. I don't know why I thought it's a good idea. Okay, so we also have to provide this thing in here. All right, so this is going to be SV. And in here, we'll have to do it like that. Okay, so, and we've got 26. Would you look at that? We've got 26, so here is 26. Okay. So, and I think that's the correct answer for the sample, right? If I'm not mistaken. It is, in fact, 26 instances of such things. And if we switch to the input, right? So let's actually quickly switch to the input and run this into, I think it has to be 470, right? So let's give it a try. Let's actually put it into our little box, and we got a gold star. How about that? Isn't that cool? I think that's pretty cool. So get ready for the bot fun. So before we go into the bot fun, we'll probably need to do a committee. So let me actually do a little bit of a committee. So let me see. So I'm gonna close the QEMO, right? So this is gonna be git status, and I probably need to sync into the host, right? So I'm gonna be syncing into the host, right? And then let me take a look at the status. STD palette. So this is not the thing that I wanna have in here, because I think, yeah, so this is the thing that I use for experimentation. Let me actually quickly get rid of it. Let me actually quickly get rid of it. So yeah, STD palette, I need to go to the home. Right, so let me do, how do you delete a file? I think it's something like del, if I'm not mistaken. Right, so it's a del, and it deletes the file. Okay, so that's actually pretty cool. So std palette txt. So I'm going to quickly remove that. So it got deleted. That's pretty cool. And now if I sync into the host, right, so sync.sh, there we go. So, and I take a look at the status. Okay, we only have that. Git status, git commit, and add day 08 part 1, and I'm gonna push that right into the repo. So if you're watching on YouTube, you can find the repo in the description. If you're watching live, I'm gonna copy paste it in chat. Right, so you can find the source code of what I'm doing in here. All right. So let's take a look at the part 2. So I'm going to predict that probably in part 2 you have to recover as much information as possible given the input, right? So yeah, I guess that's what's gonna happen. Through a little deduction, you should now be able to determine the remaining digits. Yes, consider again the first example above. Right, so here's the first example above. After some careful analysis, the mapping between signal wires and segments only makes sense in the following configuration. EED, AA, FF, blah, blah, blah. Yeah, there we go. So the unique signal patterns would correspond to the following digits. Okay, so and there you go, you recovered this sort of information. Makes sense. Then the 4 digits of the output value could be decoded as this one. Okay. Therefore, the output value for this entry is 5353. Okay. Following the same process for each entry in the second large example above, the output value of each entry can be determined like this. Okay. Adding all of the output values in the large example produces 61229. For each entry, determine all of the wire segment connections and decode for exactly what I said. It's so predictable, actually. I think in the last year, on one of the previous year, we had something similar with like a food ingredients or something like that. Does anyone remember? Right, or some sort of like a chemistry in ingredients, right? So yeah, I think it's kind of similar to that one. It's definitely cookie thinny. I don't know what you're talking about, but anyway. So when we have to do that for each individual thingy in here, what do you get if you add up all of the output values? So we need to understand here is how you can reconstruct these things. So this is 5, right? 5, 3, 5, 3, and 5, 3. Let me actually restart like my virtual machine. Let me restart my virtual machine, and so this is going to be something like this. So 5, 3, yeah, so this one is rather interesting. So that's cool. Though, oh, they could be also in a different, wait a second, is that like the same thing but in a different order? Oh, they're kind of like mixed up or something. Yeah, oh, they're kind of mixed up. I see. Right. So if I do something like, so here is the C, here is, so maybe I can put F in here. So I'm gonna put A, D, B. Okay, so they all are mixed up, which means that we can probably use masks to actually encode the state of this entire thing, right? So this is one of the things we can probably do. Right. So that's very interesting. So, and once you convert these things into masks, you can quite quickly tell which numbers are literally equal to each other, right? Which numbers are literally equal to each other? Maybe, I don't know, maybe not. After some careful analysis, the mapping between signal wires and segments only makes sense in the following configuration. So SDFB and this one are the same, right? So this is basically what we have in here. So how can we even analyze that? How can we even analyze that? Is there... That one is very interesting. Though we can quite quickly determine, you know, the unique things in the input as well, right? So then we can use that information in here too, right? So I probably need to actually sit down and like write it manually, because there's sort of like a, you know, spatial aspect to this problem, right? Which probably needs to be taken into account. Maybe, I'm not sure. I'm really not sure yet. So if I take a look at this one is always these two bars, right? One is always these two bars. So if I have something like this, just a second, so this is going to be that, all right? And I probably also want to have this table nearby, right, of the numbers, right, because I think it is rather important. So 1 is 2, 4 is yeah, so basically I just want to have that on the same screen, right? It's not like really that important, because like switching between these several screens like create friction between like context and stuff like that. 2, 5, 3, 5, 5, 5, 0, 6, 6, 6, 9, 6. Okay, so now I have that on the same screen, so there should be a little bit less friction, hopefully. All right, and then I'm gonna go in here. Okay, so if we take a look at the first thing now, right? So the easiest thing to figure out in here is AB, which is 2. Right, so AB is definitely 1, right? And that means that here, A and B, right? We have A and B, and that's basically their position in here, so we can figure that out. So the next one is probably going to be like 3. We need to find the 3 digits, which is DAB, right? So, and that's 7. Right, so we already know that A and B here is that. So that means that D goes in here, right? D goes in here. All right. That's very cool. So for each digit, you have a mapping to which segments it highlights. And you basically start with the most obvious one. The most obvious ones instantly give you. Though in case of like 1, it is very unclear whether A goes here or A goes here. So essentially what you have to write in here down is basically combination. It's either A or B, and it's either A or B. And as you add more and more information, you sort of eliminate you know, uncertainty. Okay, I can see that. That actually makes a lot of sense. Okay, so if you start with AB, you don't know which one, like in here, it's either A or B, right? So it's A, B, A, B, both of them are AB. So when you do DAB, right, so you can see if you already have something in here. So we can have A here or B in here. So that does not reduce the uncertainty, but that actually gives you this kind of information, right? So so this is the third one. Fourth one, so we have E, F, B, right? Okay, so through examples, I think I'm starting to understand what the fuck it was talking about in the description in here. So about things being mixed up. Right, I couldn't freaking understand what the fuck is it saying like in here about mixing up and stuff like that. But going through the examples actually made me understand it. Okay, I can now clearly see what you mean. This is actually pretty cool. All right. So A and B goes in here. That's cool. And here we have E and F. Right, so here is probably EF, and this one is probably EF. Right, so uncertainty like basically stays in here. Right, uncertainty stays in here. Okay, and now we have 8, which is like 7 of them, right? Which is essentially 7 of them. And this one is rather difficult. So it has A, so there's 2 things. So 8, so it can go in either of these things. This thing, okay, so we know for sure that D goes in here, all right? A is either here or here. That does not reduce the uncertainty. E goes either here or here. That does not reduce uncertainty. So I think I'm understanding. So A, C, E, D, G, F, B. Right. So A, we already reduced uncertainty in here. E, also we figured it out. D, we figured that out. C and G. So F, we have that. B, we have that. So C and G, so they go either here, C, G, right? Something like that. So uncertainty actually stay the same. So this is basically the information that we have, right? So this is basically the information that we have. And the rest of these things is essentially figuring out like this stuff, right? 2 is going to be 5. We need to find things with 5. So C, F, B. Okay, so C, right? C. We can try it 1, this thing. So we've got a subscription. We've got a subscription. Jan.
Зозик меньше, чем 3.
Jan 18383. Thank you so much. Thank you so much for 2 months of Twitch Prime subscription. Thank you, and welcome to our epic AoC and HolyC club. Okay, thank you so much. Right, and that's very interesting. So you can basically highlight these things, right? So you can say, okay, so here is C, here is D, right? C, D, F, B, right? So this is D, F, C, B. That does not correspond to anything, right? That does not correspond to anything at all. Right, so you can try like a different combination then. You can try a different combination, and you can basically sort of like try different combinations until you find something that actually fits there. Okay, so that's a very interesting way of doing that. All right. All right. So there should be like some sort of a data structure that allows you to do that quickly. And I'm thinking, is there any sense to actually think about like beat masks and stuff like that? Because I'm pretty sure the amount of combinations here is not going to be that big, right? If you know what I'm talking about, the combination is probably not going to be that big. Though, how many combinations? Like, can I just brute force everything? Probably not. It's probably not a pretty good idea to brute force anything. But that would be an interesting one, actually. So maybe the amount of input here is so small that you can brute force that, but we have like 8 things, and factorial of like 8 is probably huge, so you can't probably brute force anything in here, right? So if you do product, right, so it's gonna be, oh my god, it will take ages to actually load Haskell on this machine. It takes some time because I rarely run it, and just like it needs to warm up the caches. So it's actually 7. Though, so that's the shit we're dealing with, right? So that's the shit we're dealing with. Maybe it is not that bad to actually brute force like everything and check if everything fits or something. That would be rather interesting, right? Because there's a little bit of room for that. Right, there's a little bit of room for that, and that is fine. But I think I want to make a small break before I'll try to attempt to do anything in here. So yeah, let's make a small break, and after the break we're gonna try to come up with something. All right, so I want to have something like so. I want to have a function that you know, is capable of getting representation of the configuration, right? So we need a way to represent a specific configuration, like for instance this one. All right, so we're gonna say that this function will accept the configuration somehow, probably by the pointer. Thank you so much, Paykel1, for subscription. And then it should be able to accept the wiring, right? So it should be able to accept the wiring. And then it should return whether that corresponds to a particular number, right? So whether that corresponds to a particular number or not. In case of not of this thing not corresponding to a particular number, it may return like -1 or something like that, right? And let's actually call this entire thing like decode, right? So this is going to be decode. I hope TempleOS doesn't have a decode already taken, so it doesn't. So how can we represent the configuration, right? What's the easiest way to represent the configuration? So here we can take this as the sort of like the canonical configuration, right? So this is the first segment, second, third, fourth, 1, 2, 3, 4, 4, 5, 6, 7, right? And we can encode this specific configuration as a string of 7 numbers, A, B, C, D, E, F. right? So, and that basically represents that entire configuration. We might as well, oh, this one is interesting. So I probably cannot pass this entire thing by value, right? So I can say config, right, and something like 8 and say that, yeah, I'm going to be passing U8 and then pass that thing in there. That will be actually kind of cool. Right, and the wire could be represented as like any of those things, right? So basically this string of these things could be a wire essentially, right? And then by taking this stuff, right, so G, we would find its position and we know which segment we have to highlight essentially, right? So we'll know which segment we'll have to highlight. And in here, so wire again could be just like this thing, right? So, and the problem here is that I think TempleOS will not allow me to even compile that because it does not allow passing the arrays by values like C. Right, if I try to compile this entire thing, as you can see, it says no arrays in function arguments. Right, so you can't do that. But one of the things you can do, so we have two options. We can either pass that as like a pointer, or we can wrap this entire thing into a structure. And if we wrap it in structure, we'll still be able to pass it by a pointer, right? Because you cannot pass structures by values. So it's a rather interesting experience. So, right. And I think this is the easiest solution so far, but we'll need a way to like represent the size of the config. So let's actually create something like config size, and there will be 7 of these things. Actually not 8, it's 7. Okay, right, that's pretty powerful. All right, so, and we're basically going to iterate through the wire, right, and we're going to find the corresponding corresponding things in the wire in the configuration and maybe set some sort of a mask, right? Maybe set some sort of a mask. So this is going to be mask like so. Maybe I also want to have something like this, strlen. This is going to be a wire, right? And we also need to have something like I. Right, for I 0 less than n, so we're basically iterating through the wire, right? We're iterating through the wire, and it would be kind of cool. Okay, so I can take the character of the wire, and I want to subtract a to turn the digit into some sort of a number, right? And it would be kind of cool if the configuration was represented, so I could do something like config, right, config, and get the number of the segment that I have to highlight, which means that the configuration has to be represented slightly differently. So yeah, the configuration has to be represented slightly differently, I think. Which is rather a shame. So do I want to change the way the configuration is represented? Probably not. I'm not sure. So maybe I do. So what if I create something like class config? Is it gonna cost me too much if I do something like that? So this is a class config, and here we have like segments, right? So it's gonna be segs. Okay, and we're gonna have segs count, right? I think it makes sense to actually call it segs count. All right, so segs count, segs cnt, so it's gonna be 7. And this one is going to be the config. So this is a big conf, and this is a wire, and I can take a look at. Okay, so here's the wire. Here is a specific thing. I take a specific segment in here, and it gives me the bit that we have to set in a mask, which means that I can use this thing in a shift, right, and just do mask or, right, and that adds it to a mask. I'm pretty sure I can just do something like mask not equal, right, something like this. Okay. And then once we've got this mask, we can look up that mask in some sort of a table, right? We can look it up in some sort of a table, which will return a corresponding number, right? So yeah, I want to be able to do this kind of stuff. Right. So, and I'm not sure if I'm gonna use that in the final solution, right? Don't get wind up about me doing something wrong or anything like that. I just want to have this machinery so I can test maybe some ideas, right? So it's not necessarily the final solution or anything like that. I'm just experimenting, okay? All right, so, and that means I'll need to build up that table somehow, right? So it's going to be I64, and the -1s are going to be in that table as well. Right, so and the question is, like, how big that table should be? Probably quite big, right? So it's probably going to be quite a big of a table, because the actual numbers in there are going to be far apart. The actual numbers in there are going to be far apart. So maybe because of that, it's not particularly a great idea to do it like that. Right. So let me see. Right. So I probably need to spell this thing out in here. So this one is going to be 0. This is going to be 1. This is going to be 2. So 0, 1, 2, and this one is going to be 3. All right, so this is going to be 3 and 4, 5, 6. Right. So we can keep this stuff in here. Right. So maybe using table is not particularly great idea. That's for sure. That's for sure. That's for sure. Though, I have an interesting idea. We have a numbers from 0 to 9. Right, so we can kind of reverse this entire stuff. Right, so it means we can have like 10 in here. And in the positions of the corresponding things, we can have the numbers that you can get in the mask. Okay, so we can inverse that table, so that means we have to do that slightly differently. Right, so yeah. So this is more of a digits, right? Digits, digit masks, right? So this is digit masks, right? And we can have something like digits CNT, and we're gonna have 10 of the digits, right? So we have 10 of the digits. Digits CNT, digits CNT. Digits CNT. So, and interestingly enough, okay, 0, right? So this is the position 0, right? Then we can do something like 1, maybe 2, 3, 4, 5, 6, 7, 8, 9, right? 9. And basically start spelling things out. So 0 is basically all ones. All right, so all of 7 ones. And I wonder if TempleOS supports binary literals. Right, so basically when I want to do 1, 2, 3, 1, 2, 3, and can I do 0b? So that's very interesting. So I can probably actually check it out, right? Because I can always do something like this, where I can just print a particular number, right? 69. So here is the 69. And can I print something like 0b111? Is that a thing? I can do that. So TempleOS does support binary literals, so I can use that. I don't have to do masks and stuff like that. I can just basically hardcode this entire shit. That's very cool. Okay, that's very convenient. So here is the mask. So for the 1, we have to set 2 and 5, right? So this is more of a like that. So this is 0, 1, 2. So this is 2. Might as well actually do something like this, right? So this is going to be that. 6, 5, 4, 3, 2, 1, 0. So these are like kind of the bits that we have in here. Right. Cool. So this is going to be 2, and this one is going to be, oh my god, yeah, it was not actually correct. So it means I need an extra thing in here. So here is the extra thing. So this one is 2 essentially. Okay, so it's a little bit easier to read. Might as well actually get it a little bit closer so we can actually encode stuff like that. So pretty convenient. So 2 and 5. Might as well just pre-copy paste a lot of these things super quick. So this is going to be something like that. 2 to the 2. I'm not sure again if it's useful for the solution. So I'm just like trying to familiarize myself with the problem by playing it by playing with it around. So it's kind of like the approach that 3 Blue 1 Brown actually constantly talks about, right? So to get like to solve the problem, you just start doodling the problem around, right? You just like start drawing like different things and try different things and stuff like that, and basically familiarizing yourself with the space of the problem. So that's essentially what I'm doing, I think, not sure. Okay, 2 is gonna be 0, 2, 3, 4, and 6 if I'm not mistaken, right? So it's like 2. Right, if you spell out 2, it's gonna be something like this, right? Which is effectively 0, 2, 3, 4, 6. TempleOS, why are you doing this shit? It just can't stay. I just want it to stay. Could you please stay? Apparently it keeps jumping around for whatever freaking reason. Can you just not jump around for like a single second? Okay, so 0, 0, 2, so this is 2, 0, 2, 3, 0, 2, 3, 4, and then 6. 0, 2, 3, 4, and 6. I really wish I could just zoom in. Well, it's too much to ask apparently. Right, so I just don't want to do that. Just like I want to zoom in, and I want you to stay like that. Though I also want you to show me both of these things. I want to be able to see this thing. Why are you moving around? Like, stop moving around. Like, why? Okay, so this is because I'm moving my cursor, apparently. So when you move cursor, it just like... Oh, I see. It moves around with the cursor. I didn't know about that feature of TempleOS. That might be handy, actually, if I think about it. It's just like I have to be aware of that. Right. Which is... okay. Alright, maybe that's useful. So I'm gonna just like... This is probably the reason why it was jumping around, so that's fine. That is totally fine. Okay, so this is 3, and it's essentially 0. Right, so this is the 0. 2, 2, 3, 5, 6, right? So 0, 2, 3, 5, 6. Hopefully I did everything correctly. Right, so the next one is going to be 4. The next one is going to be 4, and let me actually see. I wish my brain just was able to visualize everything that I'm doing right now so I can just like type it out, but unfortunately I have to like help myself and constantly visualize this thing using the computer because I'm dumb. Right, like I actually jealous of people who can just like visualize this thing in their head and just type out these digits like that. I'm incapable of doing that. Like I need to like have all of that on the same screen and just connect things together. Which is horrible, like, but that's what I have to do because I'm dumb. So yeah, it's a 1, 2, then we have 3, and then we have 5, I suppose, right? So 1, 3, 5. And in here, so it could be something like, so this is gonna be 5. Right, so there we go. So I wish it wouldn't jump by this thing. Right, so 5 is essentially 0, then 1, 0, 1, 3, 0, 1, 3, 5, and then 6. Okay, so I would presume that we can cheat a little bit, and essentially for the 6 we can set all of the same segments, right? We can set all of the same segments to speed things up, because I do realize it's a little bit slow, but also set 4, right? So that's understandable. Okay, for the 7 we have to set, I think I might be able to visualize that, 0, 2, 5. Okay, I think my brain starts to accommodate to that, because I'm starting to visualize this thing and assign everything. So 8 is basically all of them, right? So I can just don't even have to think about that. So this is basically all of them. And 9 is 0, 1, 2, and 3. So this is basically the first like loop. And then 5, 6, right? So this is 5 and this is 6. Okay, so I think I typed out all of the like masks, right? So, and we should be able to actually like decode things around. Did I make any mistake in here?
HolyC is the best C.
So, right, HolyC is the best C. Thank you so much for 2 months of Twitch Prime subscription. It's Twitch Prime? Yes, it is Twitch Prime. So 0, people say 0 is wrong. Okay, so that's true, because it doesn't have 3. I think it doesn't have 3. Okay, so we have something like that. Thank you so much. You see, I'm telling you, I'm dumb, right? I cannot visualize this thing. I do realize that a lot of people actually can quite easily. Maybe a lot of people don't even need to draw this thing out. Maybe they can just do that in their head. I'm incapable of doing that in my head. So I literally have to do it like that. Sorry. It is what it is. It is what it is, and it isn't what it isn't. So for some people, one things are easy, for other people's other things are easy. So it's just like, yeah, we're different people. We are different people. Some people are dumb like me. It is what it is, and it isn't what it isn't. 9 needs to be... I don't think so. Okay, so that's totally fine. That's totally fine. So I'm gonna close the chat now. All right, so we have that, and we have an ability to actually like give a configuration, right? So give a configuration and wire things up. Right, give a configuration and wire things up. So I'm not super happy with the way we do configuration though. So, because I cannot just like visually, excuse me, visually do that. So I think I'm gonna go back with the configuration. So I'm gonna remove the config thing here. So I'm gonna remove it, and the config is gonna be the array again. So this one is gonna be something like U8, and this one is gonna be segs. All right. Just a second. It's difficult for me to like detach from QEMA and then look at what's going on here. So Dr. Drill subscribed with Twitch Prime for 6 months. Thank you. Welcome to our epic AoC in HolyC Club. Okay, let's continue. So let's actually do the segments in here. So I'm just iterating through all of the wires, right? And within those wires, I actually want to find all of these segments, right? All of these segments. Okay. So let me reorganize this stuff. So probably we'll need to do something like J. So, and in here we're gonna do J less than segs C and T plus J. Okay, so, and essentially, can I actually copy paste whatever? Oh, I cannot copy paste. Okay, that's very interesting. Oh my god. TempleOS is gonna kill me one day. Like, holy fucking shit, it's just like, sometimes it's just doing weird shit. Okay, so it's just like I don't understand. It's like, why are you jumping around? Can you just like not jump around for a single second, please? Okay, so this is gonna be something like this. What am I iterating over? I'm iterating over the segments, right? So segs cnt plus j. Okay, so this is the segments. And what I'm trying to find here, right? What I'm trying to find is if segs j equal to wire j, right? Segs j equal to wire j. And once we found that, we can use that j as the index here, right? So that's basically what I wanted to do here initially, right? So this is what I wanted to do here initially. I might as well continue looping, right? So I might as well continue looping, right? So this one is going to be more of a like a j. Right, so this is j. So because these things should be different, right? So the symbols in wire should be different, so these things should sort of never happen, if you know what I'm talking about. Unless, well, So I'm iterating through, okay, for wire I, this one has to be y. So I, we find it in the segments, right? It should be in the segments, so it's guaranteed to be in the segments. Then we set that thing, and then we do the rest of the stuff. Okay, so we might as well maybe get rid of this condition, like, and put it, yeah, it's fine. I think it's fine. Okay, so and then we've got the mask, and we can try to find that mask within the digit thing. So we're gonna do I equals 0, I less than digit cnt, right? So this is going to be digit cnt, and let me see if digit masks I is equal to the mask. What we're going to do in here, we're going to essentially return I. Otherwise, we're going to return -1, indicating that we couldn't decode that thing. Okay, so this is basically what I wanted to have, just to be able to, you know, here is the configuration, and here is the wiring. Can you recover that? So we can like play with this entire thing or something. Okay, so here's the part 1. Probably don't want to run the part 1, right? So I probably want to run the part 2. Okay, so, and let me take a look. If I try to decode, I'm gonna just try to print the following thing. So this is gonna be D. I'm gonna decode the following configuration: A, B, C, D, E, F, G. Right, so there's 7 of them, and according to this configuration, if you have C and F, right, C and F, it has to be 1, right? If I try to run this entire thing, as you can see, it is in fact 1, right? So the final result here is 1. I'm not sure if you can see that. Well, you should be able to see that. There we go. So if I swap them around, something like FC, right? So if I still run it, it's still 1. If I put something like, let's actually find configuration that doesn't make any sense, like AJ, right? AJ. If I run that, it's actually -1, right? So as you can see, it is in fact -1. So we're able to actually, you know, given a particular configuration, we can check like, you know, what's inside there. Given a particular configuration, we can check what's inside there. All right, that's pretty pog. That's pretty pog. So, and these masks maybe are going to be useful in the future as well. Maybe they're going to be useful in the future. Who knows? All righty. So Um, Probably also need to represent different things. Yeah, we'll need to store the input somewhere as well. We might start actually working on reading the input somehow. Right, so let's go ahead and do that. So this is going to be something like this. And I might as well copy-paste this entire thing. So we used to actually ignore all of the symbols in here, right? We used to ignore all the symbols, but we now need to store them somewhere. We need to store them somewhere. Where should we store them? Where should we store them? Again, here's the thing that kind of bothers me. So you have how many? Right. and it's kind of, you know, so let me take a look for each of these things. 200 lines. I mean, it's only million iterations. It's only million iterations. And we already can brute force this thing by having this function in here. So this function is super easy because you can take segments, you can start with A, B, C, D, E, F, and you can start doing all of the possible permutations, right? Take all of the possible permutations, there's only 5,000 of them, and for them, you can check if the wiring of the inputs correspond to something that makes sense. Right, so, I mean, it's only 1 million. The modern computers can do 1 million, it's just like in a snap. So, the lines are independent. Well, that's why I multiplied 5,000 by 200. There's only 200 lines, and that assuming that those things are independent, yes. Well, I mean, you can also probably... okay, so there's another n in here. Okay, multiply by 10. Right, so we have 10 millions. Okay, maybe. So, like, 10 millions is still nothing for modern computers. Like, come on. So, yeah. The question is there any permutation algorithm in TempleOS? That's the real question in here. Because like I could probably come up with some sort of like a very smart deduction thingy, but as I already said, I'm dumb, so I don't really want to do that. Okay, permutations. We don't really have permutation, but there is like a well-known algorithm of like lexicographical permutation. So we might as well maybe steal that from somewhere. Tea is boiling, yeah, so I would actually not mind a little bit of tea right now, to be fair. Maybe we'll have to make a small break. Okay, so I wonder what's causing the tea boiling, because I think this shit is like throttling my PC. What is going on? So sorted, it's as usual OBS, and also QEMA. Okay, so QEMA is doing something right now, so let's actually kill QEMA for a while. Okay, so there's not that many inputs in here, which is fine. Next, lexicographical permutation. So we can try to implement this thing. Next, lexicographical permutation, and so let's just like yoink that algorithm from somewhere. So this algorithm is rather simple, right? So you have a bunch of arrays. Find the longest non-increasing suffix, right. Are we at the last permutation already? Okay, so let array be the pivot, find the rightmost element greater than the pivot. Find the rightmost greater than element. What's interesting is that if you found the right configuration, all of the wirings are going to correspond 100% to things that make sense, right? So, and once you find that wiring, you can easily decode the outputs. That's it. So that's actually super fucking easy, right? And the size of the input is just like allows you to do that. It just allows you to do that. So we just need to implement this algorithm. It's just like, yeah, it's fucking dumb. And again, somebody's gonna be mad at me. Yeah, it's just like suboptimal solution, but you know, whatever. I'm doing that live on the stage. It's hard. So you know what? I think I want to make a small break, and I really want to like make a cup of tea. And after the cup of tea, we're gonna actually steal this algorithm. Let me actually put that algorithm in the description. Right. So, and I'm gonna put it in here because again, you just like look at the size of the data, you estimate it, and your estimates show, yeah, it is feasible, and okay, it is very cheap to implement. So yeah. All right, let's make some break. And all right, I've got even better idea. Why do we have to even generate them online? Can we just okay, in Haskell there's a pretty cool function. A, B, C, D, E, F, G, permutations. Right, so does that even exist? I think you have to include data list for that thing to work. And you've got all of the possible permutations. So you can, you know, you can save that to a file. You can save that to a file. And then just load that file from temple. So this is actually pretty cool. I don't know. So let me take a look. This doesn't look right. So why there's so few of them? But are they not lexicographical permutations? Let me take a look. So I'm gonna actually take the length of this entire thing. It's a 5004 and 40. Right. Forcing CD is still valid, yeah. To be fair, I mean, maybe this is not fair in the sense that I'm using something outside of Temple OS, alright? So maybe I'm still gonna code this thing in HolyC, right? But I'm gonna still pre-generate it. So because we can always pre-generate this entire stuff, because as you can see, it's like quite like involved and stuff like that. So you know, I might as well just like yeah, do that in HolyC as well. Though it's gonna just take a little bit more time, but I don't know. And then if you save that to a file, it's also, but we also can pre-generate it in the code itself. So we can just spend some time pre-generating the permutations and then using those permutations and stuff like that. So it's just like, I don't know, whatever. So let's implement the permutation algorithm. So I never understood the permutation algorithm, so maybe I'm gonna just steal it, right? So understanding the lexicographical permutations algorithm is on my list of to-do things, because I like never understood it for some reason. I kind of like, I read about it, I understand it, and then I forget about it for some reason. It's just like really weird. Okay. So let me define the following thing. So this is going to be something like next segs, right? So this is going to be something like sex, right? So there we go. So here is the sex. So let me just check what's going on in the chat. Okay, cool. Let me see. Something's went wrong yet again, and yeah, Temple OS is dead again, so I have to restart it. Oh boy. Okay. So first we find the longest non-lexicographical suffix. So this, in this particular case, this is the last permutation. Right, and then be the pivot. So So basically the scheme is the following, right? So you have to repeat the following scheme, but I never understood why it does it work at all. I never understood why does it work at all. Okay, so might as well actually maybe split everything in half and just put this thing in here. So, okay, so apparently we lost this thing. Okay, that's fine. Okay, so next segs. Right, U8 segs. U8 segs. Let me actually close everything in here. Just a second, like I have a little bit of a technical difficulties. All right. Okay, so that's fine. So here's that, and we're gonna have I64I, and we start with the size of the array -1. So we do know that it's a segs count, right? So this is a segs CNT. Right, so this is segs CNT -1. And while I is greater than 0, right, while we have something, it's not an array, but rather segs I-1 greater than segs I, right, so we decrement this entire thing. If, for whatever reason, I is less or equal than 0, that means we lost permutation already. So that means if you went, yeah, so basically if you went to the, like, all the way to the beginning, that means it's the last permutation, you just return false, right? So in our case, we probably want to return Boolean in here. Right, so this is going to be something like that. So this is the false. Right, so we also need an J here, which well, okay, so that's needed in here. So I64J is going to be yet again segs CNT -1. Right, and while segs J is less or equal segs I -1, we're just like decrementing this entire thing. And then we need to swap the pivot, right? So I do know that we have swap I64, so I can just use that. So it's going to be segs I -1, and I can give it the pointer, right? And then segs J. So we don't need any of this stuff. So we can simplify this algorithm quite dramatically. Okay, so and the next thing we're doing, we're reversing a particular prefix or something like that, which makes me think, does TempleOS have anything like a reverse? It doesn't have that, so we have to implement it ourselves. That's fine. Okay, so I'm gonna do J equal to segs CNT -1. Right, so actually spread that thing a little bit. And while I is less than J, I keep swapping these things around, so it's going to be swap I64. Swap I64 of segs I and segs J, right, and then it's I++ and J minus. Okay, so that's cool. And then I just return true, indicating that there is still some stuff left. So that's basically it. So we successfully stole the algorithm. I wish one day to like know this algorithm by heart, right? I like do kind of understand it, like I learn it, and then after like a couple of days I completely forget what it was all about and why it works at all. So I wish one day to understand this algorithm by heart. So, and usually I don't have to because it's just available in the standard libraries, so I can just grab it from the standard library in C++ or Haskell. And man, I remember like there was a very interesting paper that analyzed different permutation algorithms, right? So, and I don't know, I wish I could give the link or something like that. Let me actually find that. But that was such a fascinating paper, permutation algorithms. So I think you can find the link to that paper in the description. Next graphical permutation. This is not what I wanted, Chromium. Okay, so it's on Wikipedia, I think. Permutation, okay, maybe. All right. So, and let me see. Discrete mathematics. It was something like a survey of permutation algorithm. Maybe we can actually find that. Permutation algorithm paper survey. How do you spell survey? Survey. Yeah, SIRS through you, paper survey. A survey of simple. Goddamn. Permutation. So I think maybe that's one. But, okay, I cannot find that one. But the idea of that paper was that they developed a mathematical meta framework to describe all of the possible different permutation algorithms as permutational networks or something like that. Maybe you guys know what I'm talking about. Right, so, and that was so fascinating. I never actually quite found time to read that, but the idea of developing like mathematical framework of describing all of the possible permutation algorithms and just like assessing those permutation algorithms is so fucking cool, because you're basically analyzing on like a higher level. You're developing algorithms to generate algorithms of permutations. So it was so fucking cool. I read like a couple of like pages of it, and then I just put it in the back burner. I wish I could find it. So anyway, let's actually test this thing, right? I wonder, by the way, if I can modify the strings. I'm gonna assume that I can modify the strings. Right, so this is gonna be segs, A, B, C, D, E, F, G. Right, and then what we're gonna do in here is while, maybe we're gonna do it like that, do, and we're gonna print this thing. Right, we're gonna print this thing, we're gonna say something like S, what the hell is going on in here? S, segs, and then while, next, segs. Alright, something like that, and this has to be the pointer, otherwise it doesn't count. Alright, can I just generate all of that stuff? Well, I kind of tried, I just forgot the next... Well, I didn't forget anything, that's what's interesting about this entire stuff. Right, so it sort of screwed up the null terminator at the end or something. I think that's what happened in here. Let me see, because there is a 7 of them, right? So A, B, C, D, E, F, G, and I don't really know what happened. Why did it screw everything up? So it could be because I made a mistake somewhere. It could be because of that. Alright, so next permutation. Let me double check everything. So this is... Okay. So I starts as -1 and while is greater than 0, and I minus 1 is greater or equal than I, so I just decrement and go there, and if it's less or equal than 0, this is straight up false. Then I start with J, and while sex J is greater than equal I minus 1, I decrement the J, okay, then I swap. So what exactly swap? I minus I and J, that makes sense, so J starts yet again in here. And I basically keep swapping sex I and sex J. I plus plus, J minus minus should be fine. So I retype this entire thing correctly. Oh yeah, thank you so much. It has to be U8. Yeah. Thank you, chat. Very cool. Now we're talking. And... Wait, why is that it? It shouldn't stop. A, B, C, D, E, F. This is not it. This is not correct, by the way. This is straight up not correct. So this is not enough. So this algorithm is not correct. That's what I'm getting, right? Okay, so I think I'm wasting on this algorithm too much time, so that means the time has come to actually ditch it and just like do the stupidest possible thing. Right, so fuck that. Alright, so let me mount this entire stuff. So this is gonna be AoC 2021. And let's go to here. Right, so this is gonna be home. AoC 2021 08, and then I'm gonna go to GHCI. A, B, C, D, E, F, G, right, so this is gonna be 7, and then I'm gonna do plus data list, right, so I'm gonna do that. Yeah, GH, permutations, alright, so the amount of these things is, you know, 5,000, stuff like that. We can do unlines, that will give us huge string. The size of that string is like, yeah, so this is basically the size of the string, 40 kilobytes, and we can write that into file, right, so segs txt, so we actually have to do something like this, segs txt, there we go. So and if we take a look at the segs txt, here are all of the possible permutations in here, so that's fine. So, and we have 5,000 of them. So it's kind of cool that you can use Haskell to quickly generate this kind of stuff. So Haskell is great for prototyping, not really great for like actual production software, but for prototyping. So, and yeah, let me unmount or maybe run AoC one more time. So that thing should be available in our temple now, and we should be able to just you know, read it. So I'm gonna go to here, right, and go to here. So here are the segs, right? So here are all of the segments in here. Cool. So I'm wondering how difficult it is to read all of that into memory. So will it fit in the memory? It should actually fit into the memory, so should be fine. 08 main.hc. So let me quickly just take this stuff. Sex BCD. So I'm thinking how I'm gonna be actually doing all of that. I can try to do the following thing. I can have SV of sex, right? And so sex CNT is not a correct thing to say anymore, I think. Sex CNT is more of a sex size. We have a raid from Supinic. Thank you so much for raiding, and everyone who came from Supinic. How do you like my Riced Temple OS? This is Temple OS, by the way, if you're, you know. So, yeah. This is actually pretty cool. So if only Temple OS had like a good theme, maybe people would use it more. Am I right? Dark mode Temple OS. So yeah, for anyone who's interested on how to set the dark mode for Temple OS, so this is how you do that. So there's a functionality in Temple OS called gr palette set. Right, if you know how to use Temple OS, just try to find this function, and you essentially set this palette to this, you know, to this theme. And this is the theme that I stole from Groovebox theme. Right, so you just set it, and there is a little bit of a hack which forces you to sort of mem set this Groovebox theme to the standard palette, otherwise the Temple OS will constantly try to reset it. But the problem for that, it actually works quite solid. So, and you can find the source code of this entire thing in the description if you're watching on YouTube, but if you're watching live, there's this repo. There's this repo, and yeah, so it's in home theme. So you can just copy paste it into your Temple OS configuration if you want. Anyway, so yeah, it's literally Groovebox. It's like literally Groovebox. Anyway, so let's do AoC. We already have the following thing. So I'm gonna find segs CNT, and I want to replace it with segs size. Right, so I'm gonna also do replace, and okay, so this is gonna replace, And I guess that's it. So we don't really need next segs anymore. Right, you don't need next segs. So and the reason why I want you to have that is because I want to define segs count, right? So the segs count is basically 5,000 of those things, right? So we can have the segments now. So we can also call that all segs, segs count, right? So this is basically it. And I want to have a function that reads all of the segs. So u0 read all segs. Right. There we go. So we've got a rate from the Prime Agent. Thank you so much for rate, and everyone who came for the Prime. I hope I pronounced your name correctly. I'm not sure how to pronounce it. So yeah, we're doing AoC in HolyC literally, right? So this is the temple OS, and you can find the source code in here. All right, so let me see. Read all segs. So we have to do a read file. It's actually file read. It's actually file read. And so how did I call that file? I don't quite remember. I think I called it just segs.txt. Right, so we're gonna have something like size. We have to be a little bit careful though. Yeah, so it has to be size. All right, so that's fine. And here, this one is going to be something like SV begin, right? SV begin, SV, and then we're going to have something like U8, saved begin, right? So SV begin. So then later you can free this entire thing because HolyC doesn't have a RIAI. I don't know how to pronounce that. It's actually saved, saved begin. Right, it is a saved begin. Okay. So while SV size is greater than 1, we're going to be reading all of that like by words, right? So everything is separated with new line, right? So it's separated with a new line. That means I can do SV chop. Yeah, I have to have a counter. I have to have a counter. So it's I64. CNT initially 0, right? Right, might as well do something like this. For CNT equals 0 initially, so this one could be something like this. Oh boy. And then plus CNT, SV chop word, we're chopping it from SV, and then we're chopping it into the word. That means I'll have to allocate this thing in here. Right, here's the word, and then there is additional new line that I have to get rid of, so it has to be SV chop left, right? So this is something like that. Okay, so, and it's not really a word, so what I have to do in here, I think the easiest way to do this kind of stuff would be to do all segs CNT++, right? And at the end of this process, right, we can do something like you know, D segs red, and we can do just CNT. There we go. That's pretty cool. Since we're, why do I need to increment that? I'm an idiot. So I just can do that with that. All right. So we don't need that stuff, and let's actually try to read the segs. Read all segs. And if I can try to read it. Okay. So we read 5,400 segs. That's fine. That's cool. That's epic. Cool. Nice. So, I can probably maybe print some of them, right? So if I print, it's kind of difficult to print because, yeah, whatever. We don't really care about that. So the next thing we need to do, we need to start like reading all of the inputs and everything, right? So this is the part 1. I might as well just copy paste this entire thing. It doesn't matter. I will just adapt it to my case. Okay, so reading input, saved input, we're reading the word, and here is the interesting part. So I need to have like list of all wires, right? So list of all wires, and so let me actually call it something like this. So wires, and I remember I had a constant for, yeah, digits count, right? So digits count, and it's equal to like 10 or whatnot. Right, I can use this constant in here. So digits count, did I call it CNT? Probably. And in here, I can save it as a SV, I suppose. Yeah, I can save it as a SV. So here we have a wires in here. And now, instead of having like words and whatnot, I can do the following thing. So here's that. I provide the wires I, right, and it basically saves that thing into the wires. We chop left that, and there we go. So though I think this is enough to figure everything out. I think this is in fact enough. Yeah. So now I need to have a function that accepts the segment, right, the current segment, and all of the wires, and tells us if the segment is correct. Right. Oh, this is actually very, very interesting. So how are we going to be approaching all of that? So for I, starting from there, and then segs CNT, right? So here's the segs CNT. We need something like, let me see, verify segs, right? So then I do segs I, right? So I'm verifying segs I, and then I want to provide the wires, right? I want to just provide the wires. So should be all right. Though I know exactly the size of the seg, I might as well just like give the begin, right? And I know that I'm not going to overflow because the segs has a specific like size, right? Okay, so if this entire thing is true, we want to break out of the loop, right? We want to break out of the loop. And now I contains a pointer to the segments that are correct. And we can use this entire stuff to decode the outputs, right? We can use this entire stuff to decode the outputs. Oh boy. All right. So, and that means here we'll have to maybe collect the answer into something, right? So this is going to be answer initially. Well, I mean, you can always, you know, set it to 0 here. Answer equal to 0. Right. So in here we just take 4 of these things. None of that is needed anymore. That's for sure. Okay. And now, what I do decode. I already reset I, which is a very huge sin that I committed in here, because I contains the necessary information. So this is J, this is J, and this is a J. So we decode, we provide segs I, begin, and then we have to provide the configuration. So I think the code now have to accept the string view. I think it has to accept the string view. So because of that, we'll have to do something like this. Right. So in this one is going to be the word as well, right? So this is going to be the word as well. So we decode this entire thing, right? We decode this entire thing. Hopefully this thing is going to be all right. So maybe we want to save that somewhere. Right. So I'm going to do a leap of faith, and I'm not going to check that decode returns something fishy. So I'm going to straight up assign it to answer. Answer multiplied by 10 plus decode this entire thing, and then part 2 is essentially going to be, so this is not really an answer, right? So it's a single value, right? So let's actually call it a value. I might as well replace everything. So I'm going to replace answer with value, right? So this is what we're doing in here. Answer with the value. Right, and after that, I should not forget to add that value to there's a lot of things going on in here. It's just like, even if I'm doing a very dumb approach, there's still a lot of stuff that needs to be done. But maybe that's precisely why there's a lot of stuff that needs to be done. So, Yesu, okay. So this is not really a count, right? So it's more of a answer. Okay, so this is not going to compile, for sure. Now we need to go through the compilation errors. 146, what do we have in here? 146, and it says that we don't have a verify segs. Right, so, okay, that's fine. So, though we have like wires, and I'm not sure, maybe we don't even have to do that. Yeah, because we have wires available here, so maybe we're gonna just like pass them through a global variable, verify segs, and it will accept u8 pointer segs, and here it will just return a boolean, right, indicating whether it successfully verified it or not. Oh boy. Okay, so here are the segments, and what we're gonna do in here, this one is really interesting, because I guess one of the things we can do, we can just check if each individual wire decodes to an existing number. So yeah, we can do it like that. So let me see, this is gonna be I64 less than, how is that called? Digits count, right? Digits CNT plus I, right? If wires is, actually we have to do decode, right? So this is going to be decode, this is segs, and we'll have to provide this in here. But wires are already like a string view, so we'll have to do it like that. And if any of these things, right, if any of these things end up less than 0, we just basically return false immediately. Right, we return false immediately, otherwise we just return true. Okay, so does it compile? It probably doesn't compile because that's expected. Okay, so what did it say though? What did it say? Missing, what are you talking about? Why are you missing that? You don't miss semicolon in here. Don't lie to me. Don't lie to me that you're missing semicolon. I didn't see that anywhere. It's lying to me straight up. It is lying. Oh, and this one, this is annoying. This is really, really annoying. I forgot for a second. I forgot. This mother flipper doesn't check the types. I was about to make like a refactoring based on the types, but I cannot do that in TempleOS, right? TempleOS just doesn't allow you to do that because it doesn't check the types. Let me close the chat. Okay. So, okay, the wire has to be SV, right? So the wire has to be SV. All right, so hopefully now it will do the trick. Why are you saying that there is like this thing? I don't understand. What are you talking about? What are you talking about? Okay, so what if I just do something like this? What are you talking about? 137. Oh, it's so annoying. Okay, win max. Just a second. What are you talking about? Unused. Well, I don't care about unused variable. 150. 154. Verify segments. Okay, so when I'm trying to verify the segments, that's basically what I get. But what do you say? Okay. Invalid L value, compiler error, verify segs. Okay, so it's so dumb. It's all segs. Oh my god, it's the compiler is useless. Seriously, it's just like it's not gonna help you at all. Like I keep forgetting that it's a HolyC compiler. It's not a C compiler that will actually check things. This thing doesn't check anything. It's just like very annoying. Okay, so invalid L value, and okay, so this is going to be 165. Actually, I wanted 165. Okay, value multiply by 10. So when I do decode, okay, so it again complains about that stupid thing which I don't understand. Compile. Oh yeah, it's all sex. Oh my god. All right. Holy shit. Okay, so we're getting somewhere. We're getting somewhere. This is actually very cool. Ooh. Okay. So now, oh, and because of the, okay, so maybe that was something, I'm not sure. It's just so weird. Okay, so it still complains about except missing at, don't understand. I really don't understand what you're trying to tell me. So here's the segs, and here is the wires, and I'm pretty sure I'm doing everything correct. I'm pretty sure about that. Like, I'm just 100% sure. Missing at return false. It's something... Oh my god! You know what it's complaining about? This is its way of complaining about not defined I. Freaking... Ah! Of course! It's obviously undefined I. Obviously. Holy fucking shit. Okay, so this is gonna be wires. This is annoying. This is really, really annoying. It's not helping you at all. Okay. Okay, so, and then I have to do wires I, and if I try to do this thing, duplicate member at equals, what do you want from me? Oh, I forgot that you can do that, of course, like, fucking of course. Okay, count 179. It's not 179. What are you fucking talking about? It's not 179. I know where it is, I mean, but it's not 179. So it's here. It's not one. It's like, can you even report properly, please? Okay, at least we got it compiling without warnings. This is already something. This is already something. I'm super happy about that. Shit. This is the worst compiler I've ever worked with. Like, holy fuck. Anyways. Cool. Now, so we wanna, yeah, so I see the mistake. So essentially what we have to do is when any of them are like negative, we straight up do that. Okay, so it still doesn't work, which is fine. Okay, which is totally fine. I'm not complaining about that one. So we may want to do something like this. If so I'm actually reusing I didn't think so. Okay, so that should be fine. If I is greater or equal sex CNT, right? So we might want to like print something like unreachable, right? So this thing has to be unreachable. Unreachable, right? So this is unreachable, and this is gonna be something like that. And I might as well just return from the part 1, just to indicate that, yeah, it actually reached the unreachable. So this entire process didn't work out, which is quite important, in my opinion. It is, in fact, quite important. So we read all of that into the wires. All right, we read all of that into the wires. So let me double check the segment count. Let me double check the segment count. So sex CNT. So the segment count is, yeah, this one. So that's fine. Right. So, and all segments, we might as well actually print them, maybe. We might try to print them, but I'm not sure if it's a good idea generally. But let me try to do that. Because it's very, very dangerous and very, very annoying. We might try to do that. Okay, so segs I begin all segs I is that count? I think it's a size -1, and I want to set it to 0. Right, after that, I want to try to print this entire thing just to see what's going on. Right, so all segs I begin. Right, all segs I begin. And yeah, okay, so that's fine. And it failed because we tried to touch some unexisting memory, but that's expected, more or less. That's expected, more or less. Okay, that is fine. So we're verifying the segments. So this is what we've got. And of course, that's a very important point. I forgot to pass wires by a pointer. That's one of the mistakes I did. And yeah, I forgot that this entire thing is not going to check it for you. And furthermore, it never actually complained that I'm trying to access wire as an it didn't check anything. Oh, fucking didn't check a single freaking thing. Why? Oh my god. Yeah, so yeah, you need to get rid of that now. Oh boy. So yeah, that's very cool. Thank you so much, Terry. Very, very cool. 59. So now we have to iterate not until the end, but until wire count. Right, so this is the wire count, and we're trying to access not the elements of wire. Right, you see, it doesn't check anything. It's just like, holy fucking shit. Right, so this is going to be begin and J, and that should be fine. Right, and it still complains about something. It's going to be 59. Right, so I, J, so what do you say? It's a size, it's not a count, of course. Of course it's a size. Count in part 1. Okay, so it's 1.4. It's again showing like a complete bullshit. Bullshit thingy. So something about count. Let's try to find the count. What do you want from me regarding the count? So this is not what I want. Another count. It's a part 1 count. This is not the count. Part 2 count. Is that what you want? I didn't think so. I actually don't think so. All right. So except print. That's fine. But am I trying to print something? I don't think I'm trying to print anything right now. So where str print? I'm not printing anything. Okay, so I think okay, so it is basically crashing somewhere somewhere here. Oh yeah, okay. Okay, sure. It is still unreachable, kind of. Yeah, it is still unreachable. Okay, so verify the steps, verifying the segments. So decode. I take the wires and I do stuff like that. All right, so this is the digits count. Decode. Man, I wish the compiler would check just something. Just check something. It doesn't fucking check anything. It's really painful. So we have segs, and this is J, seg size. That's fine. I see the mistake. Here's the mistake, right? So who needs the type checking if you have a divine intellect? Finally. Yes. I'm literally doing the compiler's work. Even pure assembly, even NASM has more checks at assembly time than this language. I'm so mad. This language doesn't check shit. It doesn't even check shit at runtime. You know, dynamic languages at least check things at runtime. Compiled languages check a lot of things at compile time. This language checks neither in runtime nor compile time. It's literally worst of the both worlds. Imagine a thing that doesn't check anything and at any point, neither compile time nor runtime. I'm so mad. I'm really, really mad. But it is what it is. I don't have a divine intellect to understand this. So Anyways, so what we're using, by the way, we're using input, by the way. That's very interesting. Okay, so let's actually switch to sample. Right, and the sample, it's 6, 12, 29, right? So 6, 12, 29, and it is actually correct. So for the sample, it is correct, which is kind of cool, not gonna lie. But for the input, it is also correct, and it took 3,000 milliseconds, right? It's a third of a second. The whole brute force, third of a second in Temple OS. And I wonder if it is correct thing. So let's actually see. I'm a little bit nervous, by the way. I'm a little bit nervous. I'm not sure if it's gonna work out, but 989. 989 396. Okay, so we submit that and there we go. So by the way, full brute force works at day 8. So for people who's saying in the chat, I've seen that brute force is more complicated than not brute force. Probably it is more complicated, but this entire thing is complicated even further by shady language. So keep in mind the language that I'm doing that in, right? So yeah, so that's everything I have to say about that statement. So yeah, this approach is actually work. Again, you can estimate how many things you need to do. And you can notice that brute force will just work. It just works. Like less than a second. Full brute force of all of these things. Full. Third of a second. Not that much. I hope somebody's gonna be butthurt about that. I really hope so. Anyway, so that's cool. Let's do a committee. Oh yeah, imagine advent of code, but all of the solution is a brute force. All the solution is brute force. Day 8, 9 tomorrow. Yeah. I'm already streaming for 2 hours. I tried not to stream more than 2 hours because it's too much for my mental health. So I really apologize for that. Okay, so that was fun. Let's actually maybe do part 1. Okay, both part 1 and part 2. Okay, so let's do a committee before I'll actually sign off. So yeah, git status. Probably wanna. So did I close the queue emo? Sync, and I'm gonna sync into the host. Right, so I'm syncing into the host. There we go. Alrighty. So yesu, kawaii freaking desu. Status. Should I commit the sex? Sex is actually crucial part of the solution, so I'm probably gonna commit them. Home AoC, right? Git status. All right. Add day 08 part 2. 08 part 2. Git push origin. Origin master. Right, so you can find the solution in the description if you're watching live. If you're watching on YouTube, if you're watching live, you can find all of the solutions in here. So yeah, that's it for today. Thanks everyone who's watching right now. I really appreciate it. I'm really actually surprised that brute force just worked for this one. Maybe that was actually taken into account. Maybe every solution in Advent of Code this year has a brute force solution, just in case like somebody doesn't want to spend too much time into thinking about it and they have some work to do, like, I don't know, right? So maybe there is always a room for brute force, and if you want to go deeper and come up with something more smarter, you always can do that. So it's like choose your own difficulty, like in Dark Souls, right? So Dark Souls is designed so you can basically regulate the difficulty yourself, right? So you have a lot of extra bosses with extra challenges, but you're not required to actually do them. So maybe that's the same thing in here. Who knows? Anyways, So did I push that? I think I didn't push that. Yeah, I did in fact push that. All right, that's it for today. Thanks everyone who's watching right now. I really appreciate it. I think I broke my mug. Have a good one, and I see you all maybe tomorrow. I'm not sure. Probably. We'll see. We'll see about that. And let's maybe rate somebody. Let's maybe rate somebody. Does anyone stream anything interesting on software development section of this leaky platform? No, my mug is fine. All right. My mug seems to be fine. So who should we rate? So already rated Jessica. We already rated One Lives Left. Appa 420 doing Dota. Chris Nova. What is she doing? I think she's like writing her book or something. I don't know. HolyC. Okay, let's actually rate them. So let me see. I'm gonna just raid. HolyC and. Alright, get ready for the raid, boys and girls, get ready for the raid, and I see you all next time. Love you.